Now let's start with some technical terms related to lens which you already know by now. Okay, so the principal axis which is passing through both the center of curvatures. Optical center is the center of lens, focal length is half of the radius of curvature. Okay, this diagram will give you more clarity. See, this is how we take negative signs and positive sign. All the distances which are measured in the direction of incident light, they are positive. All the distances which are taken opposite to the direction of incident light, that is negative. For example, suppose this is the direction of incident light and we have to measure the object distance and image distance from the optical center. Obviously, if I will be placing my object here, I will be getting my image somewhere here. Okay, just generally explaining. So if my object is here and I am calculating the distance from optical center, so this distance will be opposite to the incident light, that means I will be taking it as negative, whereas the image distance will be towards this direction which is in the direction of incident light, positive, right. So the first center of curvature for this surface, right, for this surface, the first surface calls for the first center of curvature and this falls for the second surface of curvature. Okay, so that is why this is first center of curvature which will be having positive radius of curvature, whereas the second surface will have a negative radius of curvature. This will be inverted for a concave lens. Now center of curvature, how they are taken, you know that you draw the spherical surface of the spherical curvature and then you find the center of curvature, you take the half, you will get the focal length. This was again an explanation of how imaginary line is drawn from the curvature thing and you find the center of curvature, you measure it and then the direction of light is taken into consideration. Now these are the important points of difference between convex lens and concave lens, that is converging and diverging lens. Please note them all. First of all, after refraction, light tends to meet towards one point which is focus, whereas after refraction light rays move away from one another but they appear to be coming from one point. Okay, so you, instead of these lines you can also write after refraction light rays converge towards the focus, after refraction light rays appear to be coming from focus but they are diverging from each other. The image formed can be real in case of convex lens, write out the point, the image formed can be real, virtual, imaginary, magnified, diminished, everything. They all depends on the position of object, whereas in concave lens the image formed is always imaginary and diminished. This is a very important point. Now what are real and what are virtual images? See, suppose this is a convex lens, let me take a diagram of convex. Suppose this is a convex lens. Okay, whatever object was placed here and the principal axis, the image is formed at focus. Suppose if it is not forming on focus, it is forming anywhere, here, here, anywhere. So I can take a piece of paper, I can place it here and I will see the image forming on the piece of paper. That means I have obtained the image on a screen. So real images are those images which can be obtained on a screen, but virtual images are those images which cannot be obtained on any screen because they are just virtual. That means they are not actually existing. The rays of light are actually just appearing to be coming from that point, but they don't actually do so. For example, stand in front of your mirror in your house and see your image. Now if you place any paper, cardboard behind a mirror, you won't find any image of yours on that paper because that is virtual thing. Okay, so that is the key difference between real and virtual image. I'll get you write down the points of difference as well. Now for convex lens we always take the focal length to be positive, whereas for concave we take the focal length to be negative. And lastly, it is used to correct hypermetropia or farsightedness, whereas concave it is used to correct myopia or nearsightedness. All right. Okay. What is, by the way, hypermetropia? It is a defect of eye in which an object, a person suffering from that can see distant objects clearly but cannot see nearer objects clearly, whereas the vice versa thing is myopia. The person suffering from myopia can see nearer objects clearly but cannot see farther objects clear. Okay. Now the difference between real and virtual images: a real image is formed when the light rays starting from an object meet after reflection or refraction. That is one point. Virtual image, they do not meet at all, they appear to be coming from that point. A virtual image is formed when the light rays starting from an object appear to meet after reflection or refraction. Okay. Second point, it can be projected on a screen. That means it can be obtained on a screen, whereas in virtual it cannot be projected on a screen or obtained on a screen. Lastly, it is always inverted with respect to object. That means if object is this way, image will be that way, and vice versa. Whereas virtual image is always erect with respect to the object. Now, formation of image by lenses. Now, how do images are formed? Just remember those three rays I gave you in the initial point, how to draw ray diagrams for a lens. One was coming parallel to principal axis, another was going through optical center, and one was passing through focus. Take any of those two rays, I have given you three, take any of those two rays, extend them, and you will find your image. For example, we have taken a concave lens. This is our object. Okay. Now, the ray, we have placed an object at 2f. First of all, the ray which is passing parallel, which is going parallel with the principal axis, it will pass through the focus. But concave will use the first focus, which is the virtual focus. That means it will have a negative focal length. Alright. That is why the point was included in the difference between convex and concave. So, this ray diverges in this direction, but it is coming from focal length. Anyhow, the second ray which is passing through optical center will go straight. These two are meeting here virtually, right? So, the image is formed here. Let's see a diagram of convex lens. We have taken an object between focal length and 2f. First ray parallel to principal axis passes through focus. Same principle, same sum, everything. Second one passing through the optical center goes straight. Wherever they are meeting, the image is formed. So, see the difference. These two rays are actually meeting at that point, so that is why the image is inverted. That is why this is called a real image. Whereas these two, this ray and this ray, they are not actually meeting here. The observation, if I am standing here, I am taking the observation, I will find that this ray is definitely coming from this point, because this will be an illusion, because the ray is getting refracted at this point, right? So, these two rays are appearing to be coming from that point, but they are not actually coming from that point, and that is why these two rays are meeting virtually. So, the image was virtual image, and that is why it is also erect. So, now you can also see the third difference was the this position is erect with respect to object, whereas in this case position is inverted with respect to object. These are few diagrams which define the position of object and image for a convex lens. We should have start with the focus thing, but I will start from here. The object is placed at f, the ray parallel to principal axis passing through focus and the ray passing through optical center go straight. They will both go parallelly and the image will be formed at infinity. So, remember, make a diagram of a table. This is position of object, position of image, and size of image. So, first of all, we have kept object as focus, image is formed at infinity, size is what? Highly enlarged, because the size of image depends on where the rays are meeting. Suppose these two rays have met here, so the size is this much. Suppose these two rays are met here, so size is this much long, but they are meeting at infinity, that means size is supremely large. Then take it backwards. Now then place it between f to 2f. The image has shifted where? The image has come closer from infinity to 2f within that range. So, when object is placed between f to 2f, image has shifted from infinity to 2f, it has come closer, and size is still enlarged as compared to the object. So, enlarged. But if you will place it at 2f, where is 2f diagram? The 2f is this one. If you will place it at 2f, you will find that image is obtained at 2f and it is of equal size. So, see the pattern. You are bringing the object, no, you are taking object farther from focus to infinity, and image is coming closer from infinity towards focus, and the size is getting diminished. So, highly enlarged, enlarged, equal, so this time it will be diminished, right, because it has already obtained the equal size. So, this time it will be placed between 2f and f, right, 2f to infinity, because we are taking the object farther away. So, 2f to infinity, this will come down between 2f to f. See this diagram, beyond 2f, the image has come between f and 2f, and the size is diminished. Lastly, if you place it at infinity, all the rays which are coming from infinity are supposed to come parallel, and the parallel rays meet at focus. That means image is forming at focus. So infinity is forming at focus, highly diminished, because all you are getting is a point image. You are not even seeing a height of the image, it's a point image, so it is highly diminished. This is the pattern which is followed by a convex lens. But there is one more diagram in this, which is, I think it is not given, it is given here. When the object is placed between optical center and focus. So when object is placed between optical center and focus, the ray parallel passing through focus, optical center goes straight. If we extend them both, the rays will meet virtually in the backward direction. That means it will also have a virtual image. So between F and optical center, we have beyond F basically in the same side, and it will be enlarged and it will be a virtual image. So all of these cases are for real image, whereas there is only one case for virtual image. In case of concave lens, you will always find a virtual image only. So this is the table which I have drawn for you. Instead of that, it is same thing for convex, inverted, smaller, bigger one, two focal length. It is same where the position of object is kept and the position of image has been described. Now, last topic in this chapter is called power of a lens. What do we mean by power? See, power is something which defines how much resolution can this lens bring, or how finally it can resolve the, or how enlarged it can show us an object. So all these things are related with the power, and power has a very simple formula which you must have already seen. That power is 1 upon focal length. So power of a lens is even defined as reciprocal of focal length. Point to be noted here is that the focal length should always be in meters. That means, first of all, write it down. Power is defined as reciprocal of focal length, but it has to be in meters. For example, suppose I have a convex lens of focal length 25 centimeter. So first of all, I am going to convert it into meters, which is 25 over 100 meters, and then power would be 1 over 25 by 100. That means 100 over 25, that means 4 units. And what is the unit of power? Power's unit is diopter. It is denoted by capital D. So our answer would be 4 diopters. So see that focal length is always taken in meter to find the power of a lens. Now the important point here is, as I said in this example, that consider a convex lens of focal length 25 centimeter. If I would have said consider a concave lens of focal length 25 centimeter, the changes would have been this: negative, 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 negative and negative. That means minus 4 diopters. That means focal length is positive for convex, focal length is negative for concave, power is positive for convex and power is negative for concave. That is the point which we have written. Power of a convex lens is positive, whereas the power of a concave lens is negative. This topic concludes this chapter, refraction through a lens.